All right, I guess we'll get started. So I'm just going to finish off the array-based list implementation today, and then tell you about how to write a Makefile, and then tell you how to write a linked list. A linked stack. We're going to implement a linked stack-based. A linked list stack. All right, so we were talking about the second version of generating a string from a list. Right? So remember, this version of the function will produce the string representation of a list, printing that string representation into a buffer supplied by the caller. The caller also specifies the size of the buffer. So hopefully they specify a correct size, right? So it's up to the caller to specify the correct size of the buffer. Now the way this thing works is, we'll just start here. So I'm making a variable called buffrem. So that's just how much space is left in the buffer. Because every time you print into the buffer, you take away space in the buffer, right? So I'm going to keep track of how much space is remaining in the buffer. I'm using snprintf to safely print into the buffer. So remember that snprintf, you specify the maximum number of characters that you can print into the buffer each time. Right, so the maximum number of characters I can print into the buffer is stored in this variable called buffrem. Right? Buff, the first argument, that's the array that's a pointer to a location in memory where you're going to do the printing. So I'm going to print into buff. Right? What am I going to print? I'm going to print, this is the opening square bracket, and then the first element, oh, that's not going to work. And then the first element of the list, so that's there. Right? And then snprintf returns the number of characters that were written into the buffer. Right? So I'm going to keep track of how many characters are written into the buffer using nbuff. Right? And I'm going to check if nbuff is greater than the maximum number of characters I can print, then we're done. Right? So we'll stop and return that number of characters. Right? So if I run out of space in the buffer, or if I fill up the entire buffer, we return back the maximum buffer size, right? We return back the same value that the caller passed in. Same value minus 1, actually, back here. Right? So the maximum number of characters that you can write into the buffer is their buffer size minus 1. Right? It has to be minus 1 because we need to make sure to put the trailing, because snprintf always prints the trailing null terminator to the string. All right, so decrease the number of characters that you can write to the buffer by n, right? So it's always going to be this process over and over and over again. Print something to the buffer, update the number of characters written to the buffer, update the number of characters remaining in the buffer, right? Now the tricky part here, well, the slightly tricky part here is that you have to update the pointer into the buffer every time you write. Right, so for example, when you start, right, so there's the array, or there's the array that the caller passes in using as buff. Right, so remember, buff is just a pointer that starts pointing at the first element of the array. Right, so if you write a bunch of characters into the array, right, so suppose we write the opening square bracket, and then we've got a 0, and then we've got a comma, and then you've got a space, so we've got a space, right? Then we go to print the next character into the buffer, right? You have to start here, right? So what snprintf takes in as its first argument is the pointer into the array where you want to print, right? So now I want to move buff so that it points to that element there. Okay? So it starts by pointing at the first element, but then you're going to update it every time so that it points at the next location to start printing at. Right? So that's why we add n to buff. Right? And so that's the power of using a C pointer. Right? You can add a value to a C pointer, and that advances the pointer that many elements. It moves the pointer that many elements to the right in this case. Right? So adding n to the buffer simply moves the pointer n positions forward in the array. right? And then, of course, decrease the amount of space that's remaining in the buffer. Right? And so that loop just prints out all the remaining elements of the list. Right? Finally, at the end, we can print out the closing square bracket, right? And then return the number of characters that we ultimately printed into the buffer. All right, finally, the last function. This is incorrect. List T free, T array. There's something missing here. Can I actually free that point? Yes, there's actually a line missing here. Pretty sure there's a line missing here. T. Okay, so the list free function is supposed to free the memory that was, all the memory that the list has used. Right? And so what does that mean? You have to free the array that the list has allocated, right? And then you have to free the space that's allocated to the structure, right? And you have to do it in that order, right? So I can't deallocate the structure first and then free the array that's in the structure, right? So deallocate the memory used by the array, right? And then deallocate the memory used by the by the structure, right? When this function returns, the caller can no longer dereference the pointer that they passed in, right? So in other words, they can't use the list anymore. If they try to do so, that's undefined behavior. So save that, and I think there's a little demo program here somewhere. Where did I store it? There's list C. Is there a list demo? Okay, so here's the list demo program. It's just going to start out by making an empty list, right? It's going to print out the size of the list. We're going to add 15 elements to the list. We're going to print out the list. Add 15 more elements, remove the elements from the list, insert the elements from the list, and so on and so on and so forth. It looks like it's going to do a bunch of stuff. So let's take a look at what happens when we run it. Oops, sorry. No, not that. List. Sorry, I have to find out where I stashed it. Find dot. Okay, so it's there. Okay, so let's see what happens. So we make an empty list and print out the size of the list. We get 0, right? And now I'm just going to add a bunch of elements to the list. Every time I add, I'm going to print the list, right? So I'm going to call toString or list toString to get the string representation of the list every time, right? So add a 0, its size becomes 1. You have a list that's got a 0 in it, right? Add a 1, it adds a 1 to the end of the list, right? Its size becomes 2, right? Up to 15. Up to here, right? And then you start removing elements from the list, printing the list every time, right? So when I remove the 0, right, I'm going to remove element 0, right? Notice that element 0 is now gone, right? There was a 0 there, there's no 0 here, right? Its size goes down to 14, right? Remove the 1, so I'm removing the front element every time, right? And eventually you end up with the empty list again, right? And now I'm going to use insert. So instead of calling add, I'm going to call inserting at the front of the list every time it looks like. No, inserting at a random element, a random location every time. So we're going to insert the 0, get the 0, insert the 1, and it looks like it's in the randomly picked the front of the list, right? And insert the 2, again, it's randomly inserting at the front of the list. The 3 is randomly inserting at the front of the list. Insert the 4, so that's somewhere in the middle of the list, right? And so on and so on and so forth, right? Notice that the string is always generated reliably, which is good, right? And then remove the elements from the list again. Now, hopefully, this demo is set up. Okay. So in that last part, when I remove the elements from the list, this is where I'm using the second version of list to string, right? So I make my own character buffer here, right? Notice that it's only 32 characters long, so that when it prints out the list, right, at most it can print 31 characters of the list, right, of the string representation of the list, right? And so notice this actually works the way it's supposed to, right? So it prints up to 31 characters into the string and then stops, right? So that list has a size 14, so there should be a bunch more elements down here, but you can't see them because the buffer that I passed in isn't big enough to store the characters. right? And that's exactly the way that you want that second version of the function to work, right? You don't want the function to try to print out the remaining characters of the list, of the string representation of the list, right? Because that would go past the end of the buffer that I supplied to the function, right? So it looks like that second version of toString works the way it's supposed to. There's another notable part of this demo. So in here, I print out the, list to string, right? So I print into this buffer here. That's a locally allocated array, so I don't have to free it after I'm done with it, right? Using this version of the function, I can reuse that array every time, right? So the string representation always goes into this buffer. If you look at the previous examples, they use the first version of list to string, right? So that version of list to string dynamically allocates a character array every time, right? And then returns a pointer to the array, right? So every time I call that function, right, I have to remember to free that pointer when I'm done with that string, right? If I don't free that pointer every time, then the memory allocated to the string never gets freed, right? And eventually that could lead to running out of memory. Right, so that's the difference between those two versions of the list to string function. Right? One requires the caller to remember to always deallocate the memory. Right? The second one requires the caller to allocate the memory themselves, but then they don't have to make a new. They don't have to worry about deallocating the string every time. Alrighty, so that's I think that's all I need to say about the list, about our array-based list implementation. Right? It is worth going over the implementation again to make sure you understand what's going on. Not so much the string generating methods, right? These are here to illustrate the fact that this is what you have to do if you want to try to generate the string representation of something in C, right? They don't make for good exam questions, right? Asking you this on an exam would be horrible. Right? It would be horrible to mark, let alone write. But the other functions are pretty important because they all really test your ability to work with memory and to work with arrays and pointers. Right? All of which are fundamental in the C language. So what are we doing next? Makefiles. Oh yeah, right. I should tell you how to compile this thing. Okay. So when you compile the demo program, right? So we're in a bit of a different situation now than we were to begin with, right? So here we've created a list data type, right? So we've got list.c, we've got list.h, right? We have a separate program for the demo program, right? So that's listdemo.c, right? So when you compile this thing now, right? Compiling it is a little bit different than I was showing you before, right? So there's a bunch of different ways to compile this program. Notice that there's a list.o file in my directory. That's the compiled version of list. Right? Now list.c doesn't have a main function in it, right? So you can't run the compiled version of list. So to compile list.c, you can write gcc just list.c. Right? You don't write -o some file name, right? Because there's no executable program being created. Right? So I can simply compile that list. What happened? Undefined reference to May. Oh, sorry. I screwed that up. GCC -c. There we go. List.c. Okay. So you pass in the -c flag to indicate that I want to compile that file into object code. Right. So object code is just the compiled version of the file. Right? And so that silently, that runs, that produces list.o. Right? And now that you've got list.o, you want to compile this list demo program. Right? So what we would do so far is we'd write something like this, listdemo.c, like that. Right? And now it barfs. Right? So when you do that, right, it complains it doesn't know what all of these list functions are. Right? Which is no good, right? And so what you need to do is that you need to include the object file produced by compiling list, right? So I can compile the list demo program, the listdemo.c file, right? It'll produce the executable list.demo, but I have to also include the object file that contains all of the definitions for the list functions, right? And so when you do that, now it succeeds, right? But that's not the only way to do things, right? So you can also compile the list demo program separately, right? Not producing an executable program, right? So again, pass in -c to tell the compiler to compile this program into object code. That works fine, right? So in other words, the compiler can compile listdemo.c into object code, right? Even though it doesn't know the definition of all the list functions, right? To make the executable program, that's when you can type in gcc -o listdemo. Now I can pass in the object files, listdemo.o, and that works fine. Right? So there's a bunch of different ways that you can actually compile this program, right? Compiling this program now requires you to compile 2 different source code files, right? And so you can imagine that if you have a very large program made up of many, many object files, made up of many source code files, right? And there are various dependencies, that this would be very hard to do from the command line, right? And that's true. So there's a tool called Make that lets you that helps you build a program. Sorry, where's the, I don't see it, okay. Okay, so Make is what's called a build automation tool. Compared to modern build automation tools, Make is quite primitive. So there are fairly sophisticated build automation tools now for languages like Java, Python, whatever you want, right? They all have their own different set of tools. Make is the traditional tool for C and C++. There are more modern versions. There are different versions. There are different build automation tools for C and C++. Okay, so what Make does is that it automatically builds programs and or libraries from your source code files, right? So in other words, you can run Make on your C files, and Make will automatically build a program from those C files. Now the way it does this is that it reads something called a Makefile, which you have to create, right? That specifies how the program or library should be built, right? So Make is essentially a small little language that describes how to build a program, right? To use the language, you need to understand how Make works, right? Make was created, so if you actually hit that link and read about the history of Make, there are some interesting facts and quotes from the person who made the program. If you want to read the documentation for Make, you can just hit that link there. Okay? I'm only going to show you the simplest version of writing a Makefile. You can write extremely complicated Makefiles. So what's a Makefile? It's just a plain text file that tells Make what to do. That's it, right? So Make reads the Makefile, and then it follows the steps in the Makefile. So in a simple Makefile, right, the Makefile consists of what are called rules, right? So one or more rules, and a rule simply has the following form, right? There's something called the target, so that's the thing that you want to build, right? The target has some prerequisites, so those are the things that need to happen in order to build the target, right? And then it's got some steps, right? So then it's the recipe to build this target, right? So recipe step 1, recipe step 2, recipe step 3, and so on and so on and so forth. Notice the indenting here. That thing right there, right? That's actually a tab, right? That's not 4 spaces, it's not 8 spaces, it's a tab. If it's not a tab, Make will barf, right? It won't do what you want it to do. So it has to be a tab, right? There's a quote in the Wikipedia article that explains the tab and why it was a bad idea. So it turns out it turns out making this a tab is terrible, right? Because when you look at the Makefile, it just looks like spaces. So people will put in spaces instead of a tab, and then Make will barf, right? So that thing in red's important, right? Make sure that it's a tab. Okay. So if you want to use Make to build a C program, right? The very first rule in your Makefile describes, the first rule can define how the executable program should be built. Right? So if I want to build the list demo program, then the first rule in my Makefile is going to be, how do I build the list demo program? Right? So make calls the first target the default goal, right? So the very first target in your Makefile, that's the thing that make will try to build by default, right? Unless you tell it otherwise, right? So you can tell make to build something else, right? But if you don't tell make anything, it tries to build the default goal. The prerequisites for your goal, those are just the files that are used to create the target, right? So for listdemo.c, my prerequisites are going to be list.h, list.c, and listdemo.c. The recipe contains the commands needed to build the target given the prerequisites, right? So assuming that the prerequisites exist, the recipe will then run the commands needed to build the target. Right? So here's the hello world program, right? So you could write a Makefile for the hello world program. Right? A comment in make is just the starts with the hashtag or the pound symbol. Right? We start out by defining the target. Sorry, it's going to skip. Okay. Right, so there's my target called hello1. Right, you can give this whatever name you want. Right, no spaces in it. So that's whatever name you want. Right, so that's the name of your target. Colon. Right, the files that you need in order to build the target. Right, so what do I need to build the hello world program? I need the file hello1.c. Right, so hello1 depends on the file hello1.c. Right, now this is the cool thing about make. Right, so if you change hello1.c, right, so if I change it, I edit it and save it again, and then rerun make will automatically rebuild the target. Right, so whenever you change one of the whenever make detects that you have changed one of the prerequisites, make will automatically rebuild the target for you. Right. If you don't change any of the prerequisites and you run make again, make won't do anything. Right? It'll say that the target's already built. Okay? All right. The next line is just the recipe that you use to build the target. Right? So how do I compile the program? Well, it's just gcc hello1.c minus o hello1. Right? This name here does not need to match that name there. Right? This is just the recipe that you're going to use to build. Right? This name can be anything. Right? So that's a very simple Makefile. Okay. So what about the list demo program? Right? So for the list demo program, there's lots of ways that you can write this Makefile. Okay, so the example that I'm going to use, this is shown here. So for the list demo program, right, I'm going to assume that the object files exist. Right? So in other words, I'm going to assume that list.o exists, listdemo.o exists. Right? Given the prerequisites, how do you build the program? Well, I run the compiler. Right? Use -o to create the list demo program. Right? And then I just list the object files as arguments to the compiler. Right? And so there's the start of the Makefile for list demo. Right? So list demo depends on the files list.o and listdemo.o. If one of those files needs to be rebuilt, right, then make will also rebuild list demo. Right? So in other words, if make detects that I need to modify list, so you're going to see later on that I'm going to have a rule for list.o and another rule for listdemo.o. Right? The rule for list.o, the dependencies will be list.c and list.h. Right? So if I change list.c or list.h, right, that forces list.o to be rebuilt. Right? If list.o needs to be rebuilt, then make will automatically rebuild the list demo as well. Right? So make attempts to manage all of the dependencies for you. Okay, so that's how, that particular recipe simply says link these two object files together to produce the executable program. So in most C programs, the prerequisites for the overall target also need to be built, right? Because the prerequisites are usually object files. You can define a rule to build each prerequisite if needed. Right? So how do I build list.o? Right? So to build list.o, right, I need list.c and list.h. Right? How do I build list.o and how do I build list.o from list.c and list.h? Well, I just compile list.c. Right? What about listdemo.o? Well, I need listdemo.c and list.h. Right? Why do I need list.h here? Because listdemo.c includes list.h. Right? One of the first lines in listdemo.c is include list.h. Right? So if list.h changes, I have to rebuild listdemo.o. Right? If listdemo.c changes, I have to rebuild listdemo.o. Right? How do you build listdemo.o? Well, you just compile listdemo.c. Right? To build the default goal, you simply run the command make. So all you do is type make, and then make reads the makefile in the current directory and begins processing the first rule. Right? So if I'm in the directory that contains this makefile and I type make, right, on its own, then make will attempt to build listdemo. Right? Now, before running the recipe in the first rule, make will process the rules for the prerequisites of the first rule. Right? So make reads the dependencies, right, or the prerequisites, right, and it asks, does list O exist? Right? If list O doesn't exist, it runs the rule for building list O. Right? So it tries to compile list.c. Right? It then reads the dependency. It then sees the prerequisite listdemo.o. Right? If listdemo.o does not exist, right, it then runs the rule for listdemo.o. Right? Now, it's also the case, right, that if list.o exists, right, but one of its prerequisites for list.o, if they have changed, right, then make will automatically rebuild list.o. Right? So it will actually go through recursively and look for all of the dependencies. Right? So it'll look for the file that's changed. If a file has changed and is a prerequisite for one of the targets, it rebuilds the target. Right? So rules for the targets that the goal does not depend on are not processed unless you tell make to do so explicitly. Right? So in other words, you can put a rule into your makefile that doesn't actually affect the target program. Right? So for example, you can have a rule that builds a second program that's not related to the default program. Right? Make will never process that rule unless you tell it to do so explicitly. If a target already exists, make will rebuild the target only if the prerequisites for the target are newer than the target. Right? So basically what make does is it looks at the timestamp on the file and determines is the timestamp on a prerequisite newer than the target. Right? So if, for example, back here, right? So if make looks at the timestamp for list.o, right? So suppose the timestamp for the list.o is after the currently existing list.demo program, right? So if one of your prerequisites is newer than the current target, right, than the target program, then make automatically rebuilds the target program, right? So all it's looking for is the timestamps on the files to determine what needs to be built, what needs to be rebuilt, and what does not need to be rebuilt. Right? So for example, if I edit list.h, right? So I build the program once, everything seems to, and it may or may not work, right? I find out that there's an error in list.h, and I go ahead and edit list.h, right? So what happens when that? So if I update list.h so that its timestamp is now newer than the current list.o, right? Then make automatically rebuilds list.o, right? If you change list.h though, then that's also going to affect listdemo.o. So make automatically rebuilds listdemo.o. Right? And then when you rebuild listdemo.o and list.o, right? Now these prerequisites have changed, so make automatically rebuilds listdemo. you can have what are called phony targets, right? So a phony target is a target that is not the name of a file, right? So in other words, you just give it some name, right? And it's the name for some recipe that you want to run when you make an explicit request, right? So if you want to build something in your Makefile that's not the default, you can always write make target where target is the target name, right? So here, if I wanted to force a rebuild of list.o, right, I can tell make to make list.o, right? If I wanted to force a rebuild of listdemo.o, I can tell make to make listdemo.o, right? And so here's an example of a phony target, right? So there's a target called clean, right? There's no file called clean in the program, in the directory, right? So clean doesn't depend on anything, right? If I type make clean, then it will run the recipe for clean, right? So in this case, it's going to remove the executable program and all of its object files, right? So this is something that you'll often see in a Makefile, right? There will be a clean, right? Sometimes if you write, so notice that when you're writing the Makefile, you have to list out the dependencies yourself, right? So I have to list out the dependencies for listdemo.o, I have to list out the dependencies listdemo.c, list.h, and so on and so on and so forth, right? If you have a very large program, there's potentially lots of dependencies, and it's fairly easy to screw them up, right? So in other words, you have a mistaken dependency somewhere. So when that happens, you have to fix your Makefile, right? But also, you probably have to nuke everything that's currently in the directory, right? So that's what the clean target is usually used for, right? It removes everything that's not a source code file, right? Okay, so to run the make program, it's pretty straightforward, right? So I'm in the list demo directory right now, right? So I'm going to remove all of my object files, right? Get rid of all those. I'm going to remove list. I guess I could have just typed list clean, but anyway, make clean. Okay, so there we go. So I just have my source code files now, right? If I type make automatically rebuilds everything, right? So you can see that it compiles list.c, compiles listdemo.c, and then links the object files to produce the executable program, right? Suppose I change list.h, right? So I'm just going to touch list.h, so that updates its modification time, right? If I type make again, right, it automatically rebuilds everything, right? Because list.c depends on list.h, listdemo.c depends on list.h, right? So it rebuilds both of those. That produces new versions of list.o and listdemo.o, so make automatically rebuilds the demo, right? If I type make again, nothing happens, right? It says listdemo is already up to date because none of its dependencies have changed, right? If you type make clean, that's going to remove all of the object files and the executable, right? Okay, if you want to build a target specifically, you can type in the name of the target, right? So that only builds list.o, right? And then I can make listdemo.o, right? And then I can type make, and make will only run the link, right? It'll only link the two files. It won't rebuild listdemo.c and list.c, right? And so that's the very quick and dirty introduction to make, right? Make's actually a lot more powerful than that. There's a lot of other things you can do with make. We don't actually need any of those capabilities in this course, right? But if you go and look at any open source project, any large open source project that uses C, right? Almost invariably there'll be a Makefile, and often there will be many Makefiles, right? So often the source code files will be organized into separate directories. Every directory will have its own Makefile, right? The make file for the main program the recipes will instruct make to go into the individual directories and build, and recursively build all of the targets, right? And so you can write very, very sophisticated make files. Fortunately, we don't have to do that in this course, right? But if you're interested in this sort of thing, I encourage you to go find some open source project that uses make and look at one of the make files that's there. Right? This is as complicated as you'll have to write in this course. Right? All right. Make stacks. Is this what I want to do next? Stacks using a linked list. Okay. Whoops, that's not what I wanted to do. Okay, so I now want to introduce you to making a collection of some kind using a linked structure in C. Right? Now this is pretty similar to how you would do it in Java, except instead of using references in your nodes, you're going to use pointers in your nodes. Right? I'm going to start with a stack because a stack is easier than a linked list. Right? So you all remember what a stack is, right? Everybody remembers a stack? Right? There's a notion of a top of the stack. Right? Everything that happens on a stack happens here. Right? If you add an element to the stack, that puts an element on top. Right? If you remove the element from the top of the stack, that removes the top element. Right? You can only do things at the top on a classic stack. Right? So classically, you can push an element onto the stack and you can pop an element off the stack. Right? Popping an element off the stack should be an error of some kind. Right? So push very quickly. Oh, so this is different, right? So this is different than Java. So when you push something, so C has no methods, right? So I can't take a stack variable and say stack.push, right? Well, like you would in Java. Instead, you have to write a function, right? The function takes in a stack, right? And then the value that you want to push onto the stack. Right? So the function push takes in a stack, pushes the 1 onto the stack. And in fact, it's going to take in a pointer to a stack. Right? So if you push 2 onto the stack, right, you get that. You push 3, 4, 5. Right? You end up with a stack of 5 elements. Top element's the 5. Right? When you pop, right, again, there's no way, there's no methods in C, so you have to write a function that takes in a stack. Right? So popping an element from that stack returns the integer value that's on top of the stack, right? So if I pop that, I get a 5, right? If I pop that, I get a 4. If I pop that, I get a 3. If I pop that, I get a 2. And I pop that, I get a 1, right? Stacks are widely used in computer science and engineering, right? I think you all know this already, right? If you want to reverse an array, you can use a stack, right? So for example, to use the stack class that we're about to implement, stack data type that we're about to implement, you might write something like this, right? So I'm going to reverse an array, right? Now remember, when you have a function that takes in an array, right, you need to tell the function how big that array is, right? So the way that I've chosen to do so in this example here, right, I'm passing in the number of elements in the array, right? And then my parameter is an array of size n. Right? There are lots of other ways to do this, right? You can take in a pointer to an array of int, right? And then take in the number of elements that are held in that array. Right? So to use a stack to reverse this array, I'm going to make a stack object. Right? So our class is going to be, our data type is going to be called lstack for a linked stack. Right? Linked stack init, that makes an empty linked stack, right? And returns a pointer to the stack, right? All I'm going to do is I'm just going to push every element from the array onto the stack, right? So lstack push is our push function, right? It takes in a pointer to a stack and a value to push onto the stack, right? Once I've pushed all the elements from the array onto the stack, I'm just going to pop the stack and store them back in the array, right? So I'm going to pop the n elements off the stack. Each time I pop, I'm going to store that in the index I of the array, right? And then when the function is done, I'm going to free the stack, right? You have to free the stack here because init allocates memory for the stack and its storage. So you have to free it here, otherwise you end up with a memory leak. Right? If you want to picture what's going on, you start out with this array, right? Push the 1 onto the stack, push the 2 onto the stack, push the 3 onto the stack, right? And now I'm going to pop the elements off the stack, right? So I'm going to pop the 3 and store it immediately into the array, right? I'm going to pop the, oh, there it goes. I'm going to pop the 2, right? And store it in the array. I don't know why that's an A. That should be a 1. I'm going to pop the 1 and put that into the array, right? It's because I copied an existing slide to do this, right? And now your stack is empty. Free the stack. Your array is reversed. Right? Obviously, don't do it this way because you end up with twice the storage. You end up having to store all the n elements of the array, right? Well, you don't have to do that, right? You only have to store one element at a time. Okay, so for an array-based stack, the complexity of pop is always O1. Push is in ON when you have to resize the array that's storing the stack, right? So if you were to use our list data structure that we have, right, you can use the list to hold the elements of the stack, right? Every time you add when you add something to the list and you have to resize the list, right, that has complexity ON, right? So push for a list-based stack or an array-based stack, its worst case complexity is ON, right? If you want to guarantee O1 complexity, you have to change how you store the elements, right? So we're going to use a node, similar to how we did in 124 if you took 124 with me last term, to store the elements of the stack, or the collection in this case. What time is it? Okay. So these node-based things, or these node-based structures, are very common in C, right? Because it saves you the effort of having to deal with an array, right? Of having to dynamically allocate and deallocate arrays. Dynamically allocate arrays and then dynamically reallocate arrays when you need more storage, right? So there's lots of data structures that are written using nodes, right? A linked list is a node-based list, right? We're going to do that later on. Trees, which you'll see in your data structures course, right? Those are all node-based. Those can be implemented as a node-based structure. Graphs, which you might see in your data structures course, are also usually can be implemented as a node-based structure. Right? You'll see lots of graphs in the algorithms course, and if you take the graph theory course in the math department, you'll see them again. Okay, so what does a node actually hold? Right, so it's going to store the element of our stack, right? Could also store a pointer to an element, right? So in C, you got the choice of whether or not you want to store the element, or do you want to store a pointer to an element, right? The pointer to an element, you'll see, becomes useful a little bit later on, right? For now, we're just going to store the element directly, right? Now, what else do you need in these node-based structures? You need a pointer to 0 or more other nodes, right? And those pointers are called links, right? So in a stack's just a linear collection of elements, right? The elements are arranged in a sequence starting from the top element, right? Each element is connected to the next element deeper in the stack, right? So the top element's connected to the second element's connected to the third, and so on. Right? Now the opposite's not true, right? So the bottom element is not connected to the second from the bottom element, right? So the connection only goes one way, right? So a node for a stack stores the element. We're going to store the element for now, right? And then it stores a pointer to the next node that's deeper in the stack, right? So if we have a stack of size 1, right, one element in it, our node is this thing here. Right? So it stores our int value, and it has a pointer pointing to the next node in the stack, right? So this points to null because there is no next node, right? There's your element, there's your link, right? Now remember, the link's a pointer, right? So if I push an element onto the stack, I need to make a new node to hold the element pushed onto the stack, right? So what does that mean? I'm going to malloc. I'm going to dynamically allocate a new node. I'm going to store the element in the node, right? Then I'm going to set the link of the new node to point to the current top node, right? So in other words, I want to do that, right? So there's going to be a pointer in this node that I want to set to point to the top node, right? And then I want to move the top node up, right? So I want set top to refer to the new top node of the stack, like that, right? Now, I probably want to know how many elements are in the stack, right? So I have to keep track of that as well, right? So if I'm pushing, whenever I push a new node onto a new element onto the stack, I'm going to add 1 to the count of elements on the stack. Technically, you don't have to do this, right? So technically, you can compute the number of elements in the stack every time. But it's usually more convenient to store the number of elements. Okay, so what does pop look like? So pop is supposed to return the element sitting at the top of the stack, and then it should remove that node. Right? So to pop an element off the stack, right, I want to remember that the current element is 3, right? Right, so I'm going to remember that that value is 3, right? I'm going to set this pointer, right? Top's just a pointer to a node, right? So I'm going to set this pointer to point to the next element in the sequence, right? So I'm going to move top to point to that element there. Now, how am I going to get to that element there? Right? So if top points to this node, and I want it to point to this node, the way I'm going to get to this node is I'm going to follow this link. Right? So top points to this node, right? Top next, that link's going to be called next, right? So top next is going to point to this node here, right? So that's how I'm going to follow. That's how I'm going to get to that node there, right? Now this is C, right? That node is eating up memory, so I have to deallocate that node. Right? I have to free the memory that's associated with that node, and then I have to subtract 1 from the stack size, right? To indicate that we've removed an element from the stack. Finally, you return the element that was popped off the stack, right? Okay, so let's look at the header file, and then we'll end things there, and we'll be done for the week. All right, so what's our stack going to look like, right? So we've got our include guard. We always have our include guard, right? Looks like we're going to include standard bool because something's going to return true or false, right? So there's my type def, right? So I've got a struct called lstack, right? The definition for the structure is not in the header file, right? I have a name called lstack that's an alias for struct lstack, right? So that's what that type def does, right? The type def does 2 things, right? It tells the compiler that there's some structure called lstack, right? And whenever I write lstack, I mean struct lstack, right? So it actually does 2 things. It says the structure exists, right? And it says there's a name, an alias for the structure, right? And now I've got some functions that operate on stacks, right? I've got init, right? That returns a pointer to an lstack object, right? I've got isEmpty, right? That determines if the stack pointed to by S has any elements in it, right? It's const, right? Because the function will not change the stack, right? Size returns the number of elements in the stack, right? It's also const because size should not modify the stack at all. Right? Push and pop, right? They take in a pointer to a stack. It's not const because push and pop have to modify the stack, right? Push takes in the element to push onto the stack, returns true if it succeeds, right? Returns false if it doesn't succeed, right? If it runs out of memory, right? And pop returns the element that's on top of the stack, right? And there's the end of your include guard, right? So that's what we're going to implement, I guess, in the next class on Tuesday. All right. Any questions?
I have some questions about the assignment.
Good. Yeah, no, absolutely. That's great.
So I have 2 about the twos question.
Okay.
So the first one was, I'm just not sure. So it includes, you're including like a bool in there as one of the.
Yeah.
So do we have to use that for a solution, or is it just there in case we want to?
What does that? I forget what the question actually reads as. Hang on. This is assignment 4.
I'm trying to remember, because there was a situation where I'm like, I could have used bool, but I decided not to.
Is this right? Okay. Twos. Complete the function. Print and 2 twos complement. Oh, no, you don't have to use it. Print doesn't return anything, right? And 2 twos complement does not return true or false.
Yeah, it just includes.
Yeah. Do you have to use it? No, you can use it if you want to.
Okay.
Yeah.
And then the other question I
Okay.
Actually, it was regarding, do you mind scrolling up?
There was a typo. I think I fixed it. But anyway.
Yeah, I remember I emailed you about that.
Yeah.
There's also, if you go to the bottom of the last two, where you can put a string, you show the example for given a string.
Oh, here. Yeah.
So are you okay if it shows those, if those show like floating point exception, or do you want us to correct for that so that it won't?
No, it should show that.
Okay, so you don't want us to exit it?
No. So don't bother doing the error checking. That's fine. Yeah. Yep. And I also don't know if you get that exception on Mac. So I didn't test this on Mac. On GCC on my computer, you get the floating point exception printed. I do not know if the C compiler on Mac also generates the exception. Yeah. Any other questions? There is something else that came up. I don't know, but no one's asked about it here. So in this second question, here. So that takes in a pointer to an int, right? So that you can store the value. Someone asked this in office hours. They were wondering why their program wasn't working. So they wrote the following. So they made a pointer in their main function, right? They made a pointer to an int, right? And then they called the function, right? They passed in rem for a remainder, right? And they wondered why it wasn't working. No. So that's a pointer to an int, right? That's what that actually is, right? So that's a pointer to an int. There's no int, right? That doesn't actually make an int. That's just a pointer to an int, right? If you pass that in and you try to dereference it, it barfs, right? Because there's no int object, right? So what you need to do is you actually need to make an int variable called rem, right? And then pass in a pointer to rem, right? Because now there actually is an int variable, right? So there's actually space to store the int, right? That doesn't make space to store the int. That just makes a pointer to an int, right? It lets you store an address of an int. If you want to store the int, you actually need the int somewhere, right? So don't pass in right? So when you call the function, pass in ampersand rem, right? Or make a pointer rem, right? And pass in p, right? So that's what you have to do, right? But yeah, whatever you do, don't pass in a raw pointer because it won't work, right? There's no space to store the object. In Java, that's like writing. So writing that in Java would be like writing something like string s, right? There's no string object. There's just a variable that can point to a string object, right? To actually make the string, you have to write s equals something, right? So that's the analogy. Okay. Any other questions? All right. Have a good weekend, everybody.